Welcome back to Click Future, where your future is a click away. This is the 9th episode in our Quantum Horizon series, where we explore the fascinating intersections of AI, quantum computing, and space achievements. Our planet contains finite resources, but the solar system is filled with virtually limitless wealth. A single asteroid could contain trillions of dollars worth of precious metals. The Moon harbors rare isotopes that could power fusion reactors. Mars and the outer planets hold vast reserves of water and other resources crucial for space exploration. Today, we're exploring how the convergence of quantum computing and artificial intelligence is making space mining not just possible, but economically viable, potentially triggering the next great resource rush beyond Earth. From autonomous robots that can extract resources in the harsh conditions of space, to AI systems that can identify the most valuable asteroids, these technologies are opening up the solar system's vast resources to humanity. As Arthur C. Clarke once said, the only way of discovering the limits of the possible is to venture a little way past them into the impossible. Space mining once seemed impossible. Now, it's becoming inevitable. Before we dive into the technologies making space mining possible, let's understand what resources are out there and why they're worth pursuing. The asteroid belt between Mars and Jupiter contains millions of objects rich in valuable materials. C-type carbonaceous asteroids contain water and organic compounds. S-type silicaceous asteroids are rich in silicates, nickel, and iron. And the rare M-type metallic asteroids contain extraordinarily high concentrations of precious metals like platinum, gold, and rare earth elements. One M-type asteroid, 16 Psyche, is estimated to contain $10 quintillion worth of metals. That's a 1 followed by 19 zeros. NASA's Psyche mission, launched in 2023, is currently en route to study this metallic world. The Moon offers different treasures. Its regolith contains titanium, aluminum, and silicon, perfect for construction materials. The permanently shadowed craters at its poles harbor water ice, which can be split into hydrogen and oxygen for rocket fuel and life support. And the lunar soil contains helium-3, a rare isotope that could fuel future fusion reactors with minimal radioactive waste. Mars offers abundant iron, aluminum, and titanium, plus water ice and carbon dioxide that can be processed into fuel, breathable air, and building materials. The Martian moons Phobos and Deimos might serve as mining outposts with lower gravity than Mars itself. The outer solar system contains vast quantities of volatiles, water, methane, and ammonia on moons and dwarf planets. Jupiter's Trojan asteroids, which NASA's Lucy mission is currently exploring, may contain primitive materials from the solar system's formation. We're not looking at space mining because we're running out of resources on Earth. We're looking at it because having resources already in space dramatically reduces the cost of space exploration and development. It's about building a sustainable space economy. Mining in space presents extraordinary challenges that make Earth-based mining look simple by comparison. Space environments feature extreme temperature variations. On the Moon, temperatures range from 260 degrees Fahrenheit, 127 degrees Celsius in sunlight, to minus 280 degrees Fahrenheit, minus 173 degrees Celsius in shadow. These thermal cycles stress materials and equipment in ways rarely seen on Earth. Radiation is another major challenge. Without Earth's protective magnetic field and atmosphere, solar radiation and cosmic rays can damage electronics and degrade materials over time. The microgravity or low-gravity environments of asteroids and small moons create unique mining challenges. Traditional mining relies on gravity for many processes, from drilling to material separation. And the vacuum of space means that equipment must be completely self-contained, with no possibility of atmospheric cooling. Communication delays make real-time control from Earth impractical for many operations. The light speed delay to the Moon is about 1.3 seconds each way. To Mars, it ranges from 4 to 24 minutes depending on orbital positions, and to the asteroid belt, it's even longer. Then there's the logistics. Launching equipment from Earth is extraordinarily expensive, currently about $1,000 to $10,000 per kilogram, depending on the destination. And returning mined materials to Earth presents its own challenges, from re-entry heating to landing precision. Every kilogram we don't have to launch from Earth's gravity well is a huge win. That's why in-situ resource utilization, Using materials found in space for space operations is so crucial to making space mining economically viable. Throughout history, mining has evolved with technology, from hand tools to steam power to massive automated equipment. Space mining represents the next great leap, requiring technologies that can operate autonomously in the most extreme environments humans have ever tackled. This is where quantum computing enters the picture. The extraordinary computational power of quantum computers is perfectly suited to several key challenges in space mining. First, there's prospecting, identifying which celestial bodies contain the most valuable and accessible resources. This requires processing enormous data sets from telescopes, spectroscopic analyses, and probe missions. Quantum machine learning algorithms can analyze these complex, multi-dimensional datasets far more efficiently than classical computers. They can identify subtle spectral signatures that indicate valuable resource concentrations, even from limited observational data. Once promising targets are identified, quantum computing can optimize mission planning. The orbital mechanics of reaching asteroids or other bodies efficiently is a complex optimization problem with countless variables, exactly the kind of challenge where quantum algorithms excel. In 2024, researchers demonstrated a quantum algorithm that could calculate optimal trajectories for visiting multiple asteroids in sequence, considering variables like fuel consumption, time constraints, and orbital dynamics. The quantum approach found solutions 100 times faster than classical methods for complex multi-target missions. Quantum computing also accelerates materials science research crucial for space mining. Developing materials that can withstand extreme space environments requires understanding quantum-level interactions between atoms, something quantum computers can simulate with unprecedented accuracy. Quantum computers can model the quantum behavior of materials atom by atom, allowing us to design new alloys and composites specifically optimized for space mining operations. This could lead to drilling equipment that lasts 10 times longer, or extraction processes that use a fraction of the energy. Resource processing, refining raw materials into usable products, is another area where quantum computing offers advantages. Optimizing chemical processes for extracting metals from asteroids or water from lunar regolith involves complex quantum chemistry that quantum computers can model more accurately than classical systems. While quantum computing handles the planning and analysis, artificial intelligence will be the brain of actual mining operations, enabling the autonomy required for efficient space resource extraction. Due to communication delays, space mining systems must operate with minimal human intervention. Advanced AI enables robots to make real-time decisions about drilling locations, extraction methods, and how to handle unexpected situations. Computer vision systems, powered by deep learning, can identify promising extraction sites by analyzing visual, infrared, and other sensor data. These systems can distinguish between different mineral types and assess structural integrity to ensure safe operations. Rather than single large machines, space mining will likely employ swarms of smaller robots working cooperatively. AI coordination systems allow these swarms to adapt to changing conditions and reallocate tasks as needed. Before physical mining begins, AI creates detailed digital twin simulations of the target body and planned operations. These simulations, refined with quantum computing, allow engineers to test extraction strategies virtually before committing real resources. AI also enables self-diagnosis and repair capabilities crucial for long-duration missions. When equipment inevitably breaks down millions of miles from Earth, AI systems can identify problems and either direct repairs or reconfigure operations to work around failures. The AI systems we're developing for space mining need to be orders of magnitude more reliable and adaptable than anything we've built before. They'll be operating in environments we can't fully predict, with limited human oversight, for years at a time. Early prototypes like NASA's RASOR, Regolith Advanced Surface Systems Operations Robot, are already testing autonomous excavation techniques for lunar mining. Private companies like Asteroid and iSpace are developing increasingly sophisticated robots for lunar resource extraction. As these technologies mature, a new space resource economy is taking shape, with legal frameworks, business models, and international cooperation developing alongside the technical capabilities. The legal framework for space mining has evolved significantly. The 1967 Outer Space Treaty established that no nation can claim sovereignty over celestial bodies. but it didn't explicitly address resource extraction. The U.S. Commercial Space Launch Competitiveness Act of 2015 and similar laws in Luxembourg, Japan, and the UAE have since established that companies can own resources they extract, though not the celestial bodies themselves. The Artemis Accords, first signed in 2020 and now including over 30 nations, further establish principles for responsible resource utilization. Meanwhile, the UN Committee on the Peaceful Uses of Outer Space continues to develop international guidelines. Several business models are emerging. Some companies plan to return valuable materials to Earth, particularly platinum group metals that are rare here but abundant in certain asteroids. Others focus on providing resources for in-space use, like water for rocket fuel or construction materials for space habitats. Investment in space resource companies has accelerated. Established aerospace companies like Blue Origin and SpaceX are developing capabilities relevant to space mining. Specialized firms like Planetary Resources, now part of Consensus, Deep Space Industries, acquired by Bradford Space, and newer entrants like Astroforge and Transastra are focusing specifically on asteroid mining technologies. NASA's ISRU, In-situ resource utilization initiatives for the Artemis program, aim to demonstrate oxygen extraction from lunar regolith by 2026. China's space agency has similar plans for their lunar base. These government programs are creating initial markets for space resources. The first trillionaire will likely be made in space resources, but more importantly, space mining will dramatically reduce the cost of everything we do in space, enabling a sustainable human presence beyond Earth. There are also important environmental considerations. Space mining could reduce the need for environmentally destructive mining on Earth, but it also raises questions about preserving pristine celestial environments and preventing harmful contamination. The convergence of quantum computing and artificial intelligence is transforming space mining from science fiction to emerging industry. These technologies address the fundamental challenges of operating in space, the need for autonomy, efficiency, and adaptability in extreme environments. In the coming decade, we'll likely see the first demonstration missions extracting and processing resources on the Moon. Asteroid mining will follow, potentially beginning with small near-Earth asteroids before expanding to the main belt. The economic and scientific implications are profound. Space mining represents more than just resource extraction. It's about expanding humanity's economic sphere beyond Earth and enabling sustainable exploration and settlement of the solar system. The quantum and AI technologies making this possible are developing rapidly, bringing us closer to a future where the resources of an entire solar system are within our reach. If you found this exploration of space mining and enabling technologies fascinating, please hit that subscribe button to join us on this journey through the technological frontiers shaping our future. And leave a comment below. Which space resource do you think will be most valuable to extract first and why? In our final episode of this series, we'll explore how AI, quantum computing, and space exploration are converging to shape humanity's future in ways we're only beginning to imagine. Until then, this has been Click Future, where your future is a click away.